There is a number so large that your brain will quietly refuse to process it. 4.5 billion years. That is the age of the Earth, not the age of civilization, not the age of complex animal life. The age of the planet itself, the rock, the ocean, the spinning mass of chemistry you are currently riding through space. To make that number feel real, compress the entire history of Earth into a single 24-hour day. The planet forms at midnight. Simple microbial life appears around 4 in the morning. For the next 16 hours, life is just bacteria. Single-celled organisms drifting through warm, shallow seas. Complex animals do not show up until late evening. Dinosaurs appear at roughly 10:45 at night. They exist for nearly an hour on this scale, walking, eating, evolving, dominating every continent on the planet, and then they vanish. And us, Homo sapiens, anatomically modern humans, appear at 11:59 and 58 seconds. Every empire you have ever studied, every war, every invention, every technological leap from fire to nuclear reactors, all of recorded human civilization fits inside the final 2 seconds of the last minute of the 24-hour day. So the question that scientists are now taking seriously, the question that a published paper from researchers at the National Aeronautics and Space Administration formally posed, is this: what happened during the morning? What happened during the long afternoon? What happened in all those hours between the formation of complex biology and the arrival of us? The assumption has always been that the Earth was empty of intelligence before we arrived, but assumptions are not data. And when you look at the actual data, that assumption becomes difficult to defend. Complex biology has existed on this planet for at least 400 million years. An industrial civilization like ours has existed for approximately 300 years. That gap between 400 million and 300 is so large that you could fit our entire industrial era into the geological timeline, not once, not 100 times, but more than 1,000,000 times over. The window of possible prior civilizations is not narrow, it is staggering. This is the foundation of the Silurian hypothesis, a scientific paper published by Gavin Schmidt, a climatologist at the National Aeronautics and Space Administration, and Adam Frank, an astrophysicist. The name comes from a fictional alien species, but the science behind it is rigorous, and the question it asks is one of the most unsettling in modern geology. If an advanced biosphere existed 50 million years ago, would the planet retain the evidence? Or is the Earth a self-correcting system that methodically erases its own past? The answer requires you to fundamentally change how you think about time, about permanence, and about the planet you live on. Your first instinct when you hear this is probably the same instinct everyone has. If there were others before us, we would have found the evidence by now. We find dinosaur bones from 66 million years ago. We find trilobite fossils from 500 million years ago. We find ancient microbial mats preserved in layers of rock dating back 3 billion years. Surely, if something built cities, if something manufactured tools, if something smelted metal, we would find a trace of it. The absence of evidence, your brain says, is evidence of absence. This is a logical error that stems from a fundamental misunderstanding of how the Earth actually works. You look at a pyramid and you think stone is permanent. You look at concrete and you think it lasts forever. But you are measuring durability in human years. In geological time, stone is a liquid. In geological time, concrete is just temporary grit waiting to scatter. Your entire framework for what survives needs to be recalibrated. The Earth is not an archive. It is not a museum that preserves the past for curious future visitors. The Earth is an active, dynamic recycling machine, and it has been running continuously for 4.5 billion years. Consider the mechanism of the crust. The tectonic plates are not sitting still, they are moving, colliding, subducting. The process of subduction is exactly what it sounds like. One plate slides under another and is pulled down into the hot mantle, where it melts back into magma. The ocean floor, where most sediment and debris accumulate, is continuously being dragged under and liquefied. Geologists estimate that virtually all of the current ocean floor is younger than 180 million years old. Any ocean floor older than that has been recycled. It has been erased, fed into the planetary core and returned to a molten state. Think about what that means for a civilization that might have built its infrastructure near the ocean, which is where civilizations always build. We build our ports, our trade hubs, our great cities on coastlines and river deltas. The coast is where resources are available, where trade is possible, where food is abundant. If an ancient civilization followed the same logic, their most important structures would have been built in exactly the most temporary locations on the planet. Coastal infrastructure from 200 million years ago does not just become buried, it becomes liquid. The hard drive was not corrupted, it was melted. And the continental interiors are not preserved either, they are scoured by wind and rain and ice. The Appalachian Mountains in eastern North America used to be as tall as the Himalayas. Where did that mass go? It did not disappear, it became sediment. It became sand and mud, which washed into the sea, which accumulated in layers, which were eventually subducted. An entire mountain range the size of the Himalayas erased. When you ask where are the ruins of a possible ancient civilization, you are looking for structures that have been burned, ground into powder, washed into the sea, compressed under miles of sediment, and then melted in the Earth's core. That is the scale of erasure you are working against. To feel the true efficiency of this process, run the simulation on yourself. Imagine humanity disappears tomorrow. Not a war, not a catastrophe, just a sudden cessation of maintenance. No one left to flip the switches. What happens? Day 1, power fails. Within months, the pumps stop, the heating fails, and water begins seeping into the foundations of every major structure on Earth. Year 1, biological reclamation begins. Weeds crack through pavement. Roots pry apart concrete seams. In winter, water trapped inside buildings freezes and expands, shattering foundations from within. Year 50, roofs collapse. Without roofs, interiors are exposed to rain and temperature swings. Wood rots, drywall dissolves. Year 200, the skyscrapers fall. The steel inside concrete begins to rust. Rust expands, blowing out load-bearing columns. The skylines of New York, Tokyo, Shanghai, and Dubai tumble into mounds of rubble. Year 1000, forests cover the rubble. The debris is buried under soil and vegetation. Year 10,000, a new glacial cycle begins. Ice sheets miles high roll down from the poles like planetary bulldozers, scraping the surface down to bedrock. They push the compressed remnants of every human city into ocean trenches. They grind our legacy into a fine powder called glacial flour. 1 million years. What is left? The glass has become sand. The paper is dust. The wood is soil. The iron is a faint red stain in a sedimentary layer. A visitor arriving on Earth 1 million years after our disappearance would not find a single road. They would not find a single building. They would not find a single book. They would find a thin chemical layer in the rock record, a strange fluctuation in the background noise of the planet. But wait, you might think, what about stainless steel? What about gold? What about our massive machines? This is where thermodynamics enters the picture and destroys your optimism. Nature seeks equilibrium. It hates high-energy states. Refined metal is a high-energy state. Steel is iron that has been forced into a stress configuration by removing oxygen from iron ore. Steel desperately wants to return to being ore. It wants to oxidize. Given enough time, and deep time has more than enough time, thermodynamics always wins. Every car, every bridge, every beam is slowly burning in cold, slow motion, reacting with atmospheric oxygen and returning to the Earth. Gold is stable, yes, but gold is soft and rare. If a future observer finds a gold ring after 50 million years, will the shape survive the crushing pressure of kilometers of overlying sediment? Or will it be compressed into a shapeless nugget indistinguishable from any natural gold deposit? Then consider the biological question. You might think that even if structures fail, bones remain. We found T-Rex skeletons. We found trilobites. We have detailed fossil records going back hundreds of millions of years. Surely, if another intelligent species existed, we would find their bones. Fossilization is not the standard operating procedure of the planet. Fossilization is a statistical anomaly, a rare glitch in the decomposition process. For a bone to become a fossil, it must be buried immediately in oxygen-free sediment. It must not be scavenged or scattered. It must be infiltrated by mineralizing groundwater at just the right rate. It must survive millions of years of tectonic pressure without being pulverized. And then it must be exposed at the surface at exactly the moment that a curious observer happens to be walking by to find it. Every step of that process must go right, sequentially, over millions of years. Consider the Tyrannosaurus rex, one of the largest, most robust animals to ever walk the Earth. Scientists estimate that roughly 2.5 billion individual teeth Rexes lived and died over the roughly 2.5 million year existence of the species. How many complete or nearly complete skeletons have been recovered? About 30. 30 out of 2.5 billion. Entire species of dinosaurs are known from a single tooth. Entire ecosystems have vanished without leaving a detectable trace. Now apply that to a hypothetical prior civilization. The beings that compose it live on dry land, not in swamps. They likely cremate or bury their dead in shallow soil where oxygen rapidly destroys organic matter. If that civilization disappeared today, statistical modeling suggests that in 100 million years there might not be a single recognizable fossil left on the entire planet. Not because the civilization did not exist, because the planet is extraordinarily efficient at consuming the evidence. This realization requires a fundamental shift in the logic. If we cannot find the physical ruins of a prior civilization, it does not mean one did not exist. It means the Earth has had 100 million years to clean up after it. But physical erasure is not complete erasure. And this is the pivot at the heart of the Silurian hypothesis. An industrial civilization is not just a collection of buildings, it is a thermodynamic event. It extracts energy from the environment and dumps waste products back into the system on a massive scale. You can destroy the buildings, you can melt the machines, you can erase every physical structure, but you cannot hide the chemistry, you cannot erase the atmospheric signal, you cannot unburn the carbon. The question changes. We stop asking where are their cities and start asking where is the signal in the noise. To understand why this chemical signal matters, you need to understand something about carbon atoms. Most carbon in the universe is carbon-12. It has 6 protons and 6 neutrons, and it is relatively light. A small percentage is carbon-13, which has an extra neutron and is slightly heavier. Chemically, these isotopes behave almost identically, but biologically, there is a preference. When a plant performs photosynthesis, it slightly prefers to absorb the lighter carbon-12 molecules because processing them costs marginally less energy. Every living thing, every tree, every dinosaur, every blade of grass, every human body is enriched in light carbon-12. We are, in a sense, made of the lighter stuff. The inorganic world, meaning volcanoes, limestone deposits, and the deep mantle, contains a standard balanced mix of both isotopes. This physical separation between biological carbon and geological carbon creates a measurable, readable signal. When a living thing dies and is buried over millions of years, it becomes fossilized fuel: coal, oil, natural gas. These fuels are concentrated reservoirs of ancient biological carbon-12, the light isotope, locked underground. Now imagine what happens when an industrial civilization digs up those reservoirs and burns them. They release enormous quantities of this light biological carbon back into the atmosphere in a very short period of geologically speaking. The carbon-12 ratio in the air rises sharply. The carbon-13 ratio falls by comparison. A geologist analyzing rock layers formed during that period would see this shift in the isotopic record like a flare in the dark. This anomaly has a name. Scientists call it the Suess effect, named after the physicist Hans Suess, who first detected it in the 20th century when he noticed that the carbon in the modern atmosphere was getting measurably lighter due to our own fossil fuel burning. This is the atomic barcode of industrial civilization, and critically, it cannot be eroded, it cannot be composted, it cannot be subducted. It is locked into the chemical lattice of the rock that forms during that period. A geologist 100 million years from now could drill a core sample through our era, put a chip of limestone in a mass spectrometer, and see the spike. They would know that something disrupted the carbon cycle rapidly, violently, and from a biological source. So, the protocol for finding a possible prior civilization is now defined. We do not look for gold statues. We scan the timeline for the Suess effect. We scan for moments in deep history where the ratio of carbon isotopes shifted suddenly, drastically, and in the direction of light biological carbon, at a rate too fast for natural geological processes to produce. Nature changes the carbon cycle slowly. Volcanoes release carbon, but they do it over tens of thousands of years, and the isotopic signature is different. Volcanic carbon is heavier, coming from the mantle. A sudden sharp injection of light carbon is biologically suspicious. It suggests ancient organic matter being released at industrial speed. We have now defined our target. We are looking for a thermal and chemical fingerprint in the rock record, a fever chart of the planet from the deep past. And when we apply this filter to the data we already have, When we scan the climate record of the last several 100 million years, we do not see a flat line. We see pulses, we see anomalies. We see moments where the chemistry of the atmosphere lurched suddenly in ways that geology alone struggles to explain. The most striking of these events happened 56 million years ago. It is called the Paleocene-Eocene Thermal Maximum. 56 million years ago, the Earth was already warm. There were no ice caps, forests stretched all the way to the poles. Tropical species lived in what is now Canada. The planet was a lush, warm greenhouse. And then, in a geological instant, something snapped. Within perhaps 5,000 years, possibly faster, the global average temperature spiked upward by 5 to 8 degrees Celsius. The oceans acidified rapidly. Oxygen levels in the deep sea crashed, causing a mass extinction of bottom-dwelling marine organisms. Weather patterns across the entire planet went chaotic. But the temperature shift is just the symptom. The cause is what the Silurian hypothesis finds disturbing. When scientists analyzed the isotopic record of the Paleocene-Eocene Thermal Maximum, they found a massive negative carbon isotope excursion, a sudden, violent shift toward light biological carbon in the rock record. The data says that thousands of gigatons of carbon were injected into the atmosphere in an extremely short period. And that carbon was carbon-12 enriched, it was not volcanic. Volcanoes release heavier mantle carbon. This was old biological carbon, old dead life being burned or released at a rate nature does not typically achieve. The parallel with what we are doing today is not a loose comparison, it is mathematically tight. If you overlay the graph of the carbon released during the Paleocene-Eocene Thermal Maximum with the projected graph of modern humanity burning all accessible fossil fuels, the curves align. The rate of release, the isotopic signature, the resulting temperature spike, the ocean response, they match. We are staring at a past event that did exactly what we are doing, with the same chemistry, producing the same planetary reaction. Science rightly demands that we check for natural explanations before concluding anything exotic. And there is a leading natural explanation for the Paleocene-Eocene Thermal Maximum, the methane hydrate release theory. The idea is that the Earth warmed slightly due to changes in its orbital mechanics. That slight warming reached the ocean floor, destabilizing vast deposits of frozen methane, known as methane hydrates. The methane bubbled up into the atmosphere. Since methane is a far more potent greenhouse gas than carbon dioxide, it drove rapid additional warming. The warming melted more hydrates, creating a runaway feedback loop. This is a solid, peer-reviewed hypothesis, and it explains several features of the event. But there are cracks in it. Recent high-resolution studies suggest the carbon was not released in a single smooth pulse. It came in sharp bursts, which is harder to explain with a simple feedback loop. There is also debate about whether there were enough methane hydrates on the Paleocene ocean floor to account for the full magnitude of the carbon spike, and the trigger remains unexplained. The Earth had been warm before. Why did this release happen at exactly 56 million years ago? The natural explanation is probable, but it is not proven. And through that crack, the Silurian hypothesis enters. The world in which this event occurred is worth examining closely. The Paleocene-Eocene boundary was not a barren landscape. It was a biologically rich, warm, diverse ecosystem. Because there were no ice caps, sea levels were high, creating extensive shallow inland seas that would have served as natural highways for any maritime species. Palm trees grew in what is now Alaska. Crocodilians swam in what is now the Arctic Ocean. The planet was, in many respects, a Goldilocks environment for a civilization. High biodiversity meant abundant resources. High temperatures meant a long growing season. Extensive shallow coastlines meant easy access between different regions. And crucially, because sea levels were so high during this period, the land surfaces that existed along those warm Eocene coastlines are now deeply submerged or have been eroded entirely away. The geography of the Paleocene-Eocene Thermal Maximum hides its own evidence with extraordinary efficiency. If a civilization existed then and built its infrastructure on those warm, productive coastlines, the land they lived on is now either kilometers under the ocean or has long since been subducted beneath the continental plate. The Paleocene-Eocene Thermal Maximum is the strongest candidate event, but it is not the only one. Scanning further back in the rock record, there are other anomalies called oceanic anoxic events. The oceanic anoxic event at roughly 120 million years ago, and another at 93 million years ago. These were periods when the oceans of the entire Earth suddenly lost oxygen. The deep sea became a dead zone. Black, organic, rich shale was deposited globally. The standard explanation is massive volcanic activity triggering global warming and nutrient runoff into the oceans. But nutrient runoff into the ocean causing dead zones sounds familiar. It sounds like industrial-scale agriculture where excess fertilizer washes from fields into rivers and from rivers into the sea, causing explosive algae blooms that consume all the oxygen and kill the marine ecosystem. We see this happening today at the mouths of the Mississippi River, the Nile, and the Yangtze. The pattern, carbon spike plus warming plus dead oceans, repeats across the geological record at intervals of tens to hundreds of millions of years. Going even further back, 360 million years ago in the late Devonian period, there was another mass extinction event. Unlike the asteroid that killed the dinosaurs, there is no single obvious trigger for this one. The extinction was prolonged, driven by anoxia in the oceans and rapid climate disruption. One scientific theory attributes it to the evolution of deep-rooted trees. Trees grew roots that broke apart rock and released massive amounts of nutrients into rivers. Those nutrients fed explosive algae blooms in the ocean. The algae killed the marine ecosystems. A new biological phenomenon radically altered the planetary chemistry and triggered a mass extinction event. That is also the definition of what we are doing now. The mechanism is identical. A species becomes too successful, disrupts the planetary chemistry, and triggers a cascade. In the Devonian, the driver was trees expanding across the continents. In the current era, the driver is industrial civilization. Whether the disrupting agent was a mindless root system or a thinking primate, the chemical signal in the rock is the same. But before we examine the candidates for a possible prior civilization, we need to address a flaw in the search itself. When you imagine what a prior civilization would look like, your brain immediately constructs images based on your own cultural reference points. You picture stone columns. You imagine carved monuments. You envision networks of paved roads. You are looking for a version of yourself in the past, an advanced human-style civilization using the same materials and the same aesthetic logic that human civilizations have used. This is the streetlight effect applied to archaeology. You search where the light is, not where the keys actually fell. A prior civilization would not necessarily have followed the same technological path we did. Our path, from stone to bronze to iron to coal to silicon, is a sample size of exactly one. It is the only technological trajectory we have ever observed. We have no basis for assuming it is the only possible one. Consider a civilization that mastered biology instead of physics. Rather than mining silicon to build solar panels, they might have genetically engineered broad-leafed plants to function as highly efficient photovoltaic collectors. Rather than smelting steel beams to build structures, they might have manipulated the genetics of coral or fungi to grow calcified, self-repairing buildings. Rather than burning oil for transportation, they might have bred highly efficient organisms for carrying and movement. This is what you might call soft technology, and it is the ultimate archaeological camouflage. A building grown from modified cellulose or biological secretions is indistinguishable from natural organic material once it dies. A computing system based on neural tissue decays into protein. Vehicles made of biological materials leave no rust. If a civilization flourished for 5 million years using advanced biotechnology, their entire technological infrastructure would be biodegradable. When they vanished, their machines would not crumble. They would compost. Within 1,000 years of their disappearance, their most sophisticated technology would be indistinguishable from topsoil. We might be walking through forests that are the feral descendants of their agricultural systems. We might be eating fruits that were originally engineered by their scientists millions of years before us. The absence of metal artifacts is not the absence of tools. It is simply the absence of the specific crude materials we happen to use. There is also a counterintuitive principle at work in the evolution of technology. The more advanced a civilization becomes, the smaller its physical footprint tends to be. Look at human technological history. The Industrial Revolution was enormous and messy. We built massive, inefficient steam engines. We burned coal in open furnaces. We constructed thick brick factories that left substantial physical traces. A 19th century locomotive is a very obvious archaeological artifact. It is large, heavy, and made of iron. But look at the trend of the last century. We are moving toward miniaturization. We are moving toward the cloud. Our data is not carved in stone. It is encoded in magnetic orientations on fragile drives that will dissolve in decades. A modern smartphone contains more computing power than a room-sized computer from 70 years ago, and it leaves a vastly smaller physical footprint. Extrapolate this trend over 1,000,000 years. A civilization that survives for a truly long time cannot operate on a linear economy. They would exhaust their planetary resources within centuries, as we are currently doing. To survive across geological timescales, a civilization must achieve something close to a closed-loop economy. Their waste must become their fuel. Their discarded material must be endlessly reprocessed. Their efficiency becomes, paradoxically, their camouflage. A civilization with perfect sustainability would not leave strip mines or plastic oceans or nuclear waste sites. They would look, from the outside, like a pristine natural ecosystem. They would blend back into the background of the planet. This means that the only civilizations we could easily detect archaeologically are the failed ones, the civilizations that crashed and burned, leaving a mess. A successful civilization, one that learned to live within its planetary budget, would be essentially invisible. By looking for ruins and garbage, we might be conducting a selection bias experiment, only capable of finding the civilizations that did not survive and interpreting their absence as evidence that no civilization ever existed. Now let us talk about what we can look for, regardless of the technological path a prior civilization took. Beyond the carbon isotope signal, there is a second chemical fingerprint that a large-scale industrial civilization would leave behind: nitrogen. If a civilization grew large enough to face the problem of feeding billions of beings, it would need to manipulate the nitrogen cycle. We did this in the early 20th century through the Haber-Bosch process, a method of converting atmospheric nitrogen into synthetic fertilizer. Today, roughly half of the nitrogen atoms in your body originated not from natural soil processes but from an industrial factory. This intervention dramatically expanded the Earth's carrying capacity, but it has a cost. Industrial fertilizer runoff washes from fields into rivers and from rivers into the ocean. The nitrogen acts as a superfuel for marine algae. The algae bloom explosively, then die, then rot. The rotting process consumes all available oxygen in the surrounding water. The result is a dead zone, an anoxic region where nothing can survive. We see these dead zones today at the mouths of every major river system connected to intensive agricultural regions. In the geological record, these zones will appear as sudden layers of black organic-rich shale, devoid of bottom-dwelling organisms, at the edges of ancient continental shelves. If we find a moment in the deep past where rivers suddenly delivered massive nutrient loads to the sea, causing a coastal marine extinction, we have to ask the uncomfortable question: was that a natural flood event? Or was it the runoff from a continental-scale farming empire desperately trying to feed a growing population? There is a third category of signal that a technologically advanced civilization would leave behind: the technosphere elements. Modern technology concentrates rare materials in ways that nature does not. Rare earth elements like neodymium, lanthanum, and gadolinium, precious metals like gold and platinum, industrial metals like chromium and vanadium. In nature, these elements are dispersed thinly through enormous volumes of rock, but an industrial civilization functions as a localized entropy reversal machine. It expends enormous energy digging up millions of tons of ore, extracting the target elements and concentrating them in urban centers. When a city like Tokyo or London eventually erodes into sediment, those concentrated metals do not simply vanish. They become part of the downstream sedimentary record, creating what geologists call placer deposits, layers of sediment with unusually high concentrations of specific processed elements. A future geologist drilling a core sample might find a thin band of clay where concentrations of gold, platinum, and neodymium spike to 100 times the background level. And, more critically, these metals might be found in alloy ratios that do not exist in nature. Nature creates pure gold nuggets. Nature does not create a fused alloy of aluminum, titanium, and purified silicon. Finding these elements bonded together in an unnatural combination would be a technofossil, a chemical fingerprint of manufacturing persisting long after the machine itself has rusted away. The complication is that natural processes can mimic this signal. Asteroids, particularly metallic meteorites, contain high concentrations of iridium, gold, and platinum. When a large asteroid strikes the Earth, it vaporizes and dusts the planet with a thin layer of these metals. Every time we find a metal spike in the deep geological record, we default to the asteroid hypothesis. The natural mechanism acts as a perfect mask, providing a plausible geological explanation for what might be an artificial deposit. This is the fundamental challenge of the Silurian hypothesis. Every signal we would expect to find from a prior civilization has a natural geological explanation waiting to explain it away. Carbon spike, volcanic outgassing, metal anomaly, asteroid impact, marine dead zones, tectonic-driven sea level changes, nuclear isotope anomaly, natural fission in uranium-rich rock. We might be systematically misattributing every piece of evidence of a prior civilization to entirely natural causes, because science, correctly, defaults to the simplest natural explanation first. There is one anomaly in the geological record that deserves specific attention in this context. In 1972, French physicists were studying a uranium mine in Oklo, Gabon. What they found was deeply puzzling. The uranium ore in the deposit had already been partially burned. The ratio of uranium-235 was too low. It looked, chemically, like the spent fuel from a modern nuclear reactor. The current scientific consensus is that this was a natural nuclear reactor. Groundwater seeped into a particularly rich uranium vein, acted as a moderator for the fission chain reaction, and the reaction ran at low power for hundreds of thousands of years. This explanation is physically plausible and consistent with what we know about nuclear physics. But the Silurian hypothesis asks us to consider the alternative. Was Oklo a natural phenomenon, or was it a waste deposit, a buried storage facility for the spent fuel of a civilization that needed to dispose of its radioactive byproducts? The two possibilities are not easily distinguishable from the physical evidence alone. The question of prior intelligence also extends to biology in ways that are both fascinating and disturbing. If a civilization existed long enough to master biotechnology, they would inevitably have engineered organisms. We are on the cusp of doing exactly this ourselves. With CRISPR and synthetic biology, we can now insert new sequences into living organisms, create proteins that do not exist in nature, and modify the genetic code of living systems. A civilization a million years ahead of us in this field would have capabilities we cannot fully imagine. Now consider that roughly 98% of the human genome does not code for proteins in any obvious way. This is sometimes called junk DNA, though that label has become increasingly inaccurate as we learn more about its functions. A significant portion of this non-coding DNA consists of endogenous retroviruses, the fossilized genetic remnants of ancient viral infections that integrated themselves into our ancestors' genomes and have been copied faithfully ever since. We carry the genetic ghosts of ancient plagues in every single cell of our bodies. Scientists at Harvard demonstrated in 2012 that DNA can be used as a storage medium. They encoded a 53,000-word book into a strand of DNA. The encoded information occupied a volume smaller than a grain of sand. DNA has been successfully copying itself and transmitting information for roughly 4 billion years. It is, in terms of longevity and reliability, the most effective information storage system that has ever existed on Earth. This leads to a possibility that sounds like science fiction but is grounded in real biology. If a dying civilization wanted to leave a message that would survive geological time, the only medium robust enough would be the genome of a living reproducing species. Encoded in the non-coding regions of a host organism, information could survive and be copied faithfully for tens of millions of years, as long as the host species survived. We might be carrying someone else's data. The strange repetitive sequences in our genome, the junk that we have not yet decoded, might be an archive. It might be a library. It might be a warning. But if that is true, we have a specific problem. We are the storage device, and we do not have the password. We can read the letters A, C, T, G. We cannot yet read the language they might be written in. We are walking libraries, utterly oblivious to the content of our own shelves. Now consider the candidates for intelligence that might have preceded us. Evolution does not repeat structures exactly, but it does converge on solutions. Eyes evolved independently at least 40 times in the history of life. Flight evolved 4 times. Intelligence, the ability to model the environment, predict the future, and solve novel problems, appears to be a convergent solution to the problem of survival in complex environments. Among the dinosaurs, a group called the troodontids is particularly worth examining. These were relatively small, bird-like dinosaurs from the late Cretaceous period. They had large, forward-facing eyes, indicating strong depth perception, grasping hands, and one of the highest encephalization quotients of any dinosaur group, meaning their brain was large relative to their body mass. They were highly social, organized pack hunters with what appears to have been sophisticated coordination behavior. If the asteroid had not struck 66 million years ago, what would 10 million more years of evolution have done to the troodontid brain? They already had the hardware, hands for manipulation, a brain capable of learning, social structures for transmitting knowledge. A troodontid civilization would not have built what we build. Their aesthetic, their technology, their priorities would have been entirely foreign to us. They might have used forest materials rather than stone. They might have developed in directions we cannot predict. And if they burned enough carbon, if they started clearing forests on a large scale or stumbled upon coal deposits and burned them, they would have produced exactly the kind of isotopic spike we now know to look for. The oceans present another evolutionary pathway. Cephalopods, the family that includes octopuses, squid, and cuttlefish, represent what might be called an alien intelligence already resident on Earth. Octopuses have decentralized nervous systems. 2/3 of their neurons are in their arms rather than their central brain. They solve complex puzzles, they use tools, they display what appears to be individual personalities and play behavior. The chambered nautilus is essentially the same organism it was 500 million years ago. Cephalopods had enough evolutionary time to develop in any direction. An aquatic civilization faces real physical obstacles. You cannot produce fire underwater. Without fire, conventional metallurgy appears impossible. But biotechnology does not require fire. Chemistry at hydrothermal vents, where superheated mineral-rich water creates extraordinary chemical gradients, could potentially support a very different kind of industrial process. Such a civilization might not have left metal artifacts, but it might have left chemical disruptions in the marine record, shifts in phosphorus or nitrogen cycles that look, from our current analytical framework, like large-scale natural events. There is a hard physical reality underlying all of this that the Silurian hypothesis forces us to confront directly. The Great Filter, a concept from the study of the Fermi paradox, refers to a barrier in the development of complex life that makes the emergence of a long-lasting technological civilization statistically improbable. Most discussions of the Great Filter focus on the possibility of alien civilizations in the wider universe, but the Silurian hypothesis suggests there may be a filter operating right here, on Earth, on repeat. An industrial civilization is a high-complexity thermodynamic system. To build and maintain a modern city requires a massive, constant inflow of high-grade energy and a constant massive outflow of entropy in the form of waste, heat, and pollution. This is not a design flaw, it is physics. The second law of thermodynamics does not permit exceptions. You cannot create order locally without creating greater disorder somewhere else. The resources needed to initiate an industrial civilization, specifically fossil fuels and easily accessible surface deposits of key metals, are finite. They are the accumulated savings of the planet, compressed over hundreds of millions of years. A civilization burns through these savings in centuries. We have consumed more easily accessible energy in the last 100 years than in the previous 100,000 years combined. As the easy resources deplete, the energy return on investment for extracting resources drops. You have to dig deeper, which costs more energy, which makes the economy less efficient, which makes the social structure more fragile. Then a relatively minor shock, a drought, a pandemic, a political collapse, triggers a cascade failure in a system that was already operating on razor-thin margins. In a simple, low-complexity society, that shock is survivable. In a high-complexity industrial society running at the edge of its thermodynamic limits, the same shock can be catastrophic. This is the Great Filter that operates locally. The civilizations that get big enough to leave a chemical signal in the rock record are exactly the civilizations most likely to have overextended themselves thermodynamically and collapsed. The civilizations that survived might have been the ones that stayed small and sustainable, and therefore left no detectable trace. The one-shot theory follows from this logic. Consider the resources we have been using. The coal that powered the Industrial Revolution, the shallow oil that drove the 20th century economy. These accumulated over hundreds of millions of years. They were the starter pack of our civilization, the easily accessible energy that allowed us to bootstrap our technological capabilities to the point where we could reach for more complex energy sources. If a prior civilization used those starter resources before us and then collapsed, the resources would have been depleted. A new intelligence arising on Earth afterward might have found itself in a world that appeared pristine but was actually drained. It would have the potential for intelligence, but lack the energy density needed to bootstrap an industrial revolution. But we did find oil, we did find coal in enormous quantities. This observation leads to two possibilities. Either we are genuinely the first technological civilization, and the pantry was full because no one had ever eaten from it, or the pantry refills itself, and fossil fuels are, in a sense, renewable if you wait long enough. It takes approximately 10 to 20 million years for significant new deposits of organic material to accumulate, get buried, and be cooked into coal and oil by geological processes. The intervals between the major carbon anomalies in the geological record, the Paleocene Eocene Thermal Maximum at 56 million years ago, the Cretaceous oceanic anoxic events at 90 and 120 million years ago, are in the range of tens of millions of years. The timing is close enough to the recharge time of the fossil fuel reservoir to be suspicious. Are we part of a cycle? Does the Earth produce a civilization? That civilization burns the accessible energy and collapses. The planet waits for the fuel supply to regenerate, and then a new civilization eventually emerges to repeat the process? We might not be the owners of the planet. We might be the current harvest of a very long growing season. The climate system functions as the built-in kill switch in this cycle. You cannot build a global industrial infrastructure without manipulating matter on a massive scale. You turn forests into farmland. You turn rock into concrete. You turn ancient organic material into atmospheric carbon. Every single one of these conversions releases greenhouse gases. This appears to be physically unavoidable. You cannot perform work without generating heat. You cannot industrialize without altering the composition of the atmosphere. Here is the critical threshold. The climate models for our current trajectory of fossil fuel burning predict a global temperature increase of 5 to 8 degrees Celsius in a business-as-usual scenario. That is the exact number recorded in the Paleocene Eocene Thermal Maximum. It is not a coincidence. It is the breaking point of the planetary thermostat, the temperature at which positive feedback loops, melting permafrost releasing trapped methane, loss of reflective ice cover, destabilization of oceanic methane hydrates, begin to compound faster than the civilization can respond. If a previous species industrialized and hit the same wall, they would have triggered the same sequence of events. The climate system does not negotiate. It amplifies. The response of the planet is always disproportionate to the initial forcing. You push the temperature up by 1 degree through emissions, and feedback loops push it up by 5. The civilization loses control of the response. Agricultural systems fail as weather patterns shift. Coastal infrastructure floods as ice sheets melt. The economy collapses under the weight of cascading environmental disasters. The civilization does not necessarily go extinct, but it is broken. It is knocked from an industrial age back to something more primitive. The survivors live in the ruins of a world that overheated, slowly forgetting how to build the machines until, eventually, they are simply organisms wandering through a jungle that has grown over their greatest achievements. The thermal spikes in Earth's climate record might be the fever charts of civilizations that reached for the stars, tripped the planetary thermostat, and were beaten back down by the heat. Now let us talk about what comes next. Let us project forward 50 million years. Humans are gone. The long winter has passed. A new spring has arrived on the planet. A new species has evolved to a state of high intelligence. Suppose, based on current evolutionary trajectories, that they evolved from a rodent lineage, highly social, dexterous, curious beings with hands capable of fine manipulation. They build institutions. They develop science. They invent geology. They begin to drill core samples from the rock, trying to understand the history of the world they inhabit. What do they find of us? They do not find New York City. Manhattan has become a thin layer of strange reddish sandstone embedded in a cliff face on a continent that has shifted hundreds of kilometers from where it is today. They do not find the internet. The server farms are dust. What they do find is a thin band of sedimentary rock, globally distributed, that is unlike anything else in the geological record around it. In this band, the ratio of carbon isotopes is wrong. The amount of light carbon spikes dramatically. There is an anomalous concentration of plutonium and other radioactive isotopes. Trace amounts of rare earth metals appear in alloy combinations that have no natural explanation. There are microscopic fragments of a polymer compound, a substance made of long-chain carbon molecules that appears, on chemical analysis, to be too regular to have formed spontaneously. Their geologists will argue. One school of thought will attribute the carbon spike to a volcanic supereruption. Another will argue for a large meteorite impact that vaporized carbonaceous material. A fringe researcher will raise the uncomfortable alternative that these anomalies are not geological at all, but are the chemical residue of a civilization that flourished 50 million years earlier and then collapsed. The academic community will respond with the same dismissal we use today. If they were civilized, where are their cities? Where are their bones? We find dinosaur bones from 100 million years ago. Surely if something intelligent lived here, we would find them. They will look at our layer in the rock and call it a natural climate event. They will name it, perhaps, the Anthropocene Thermal Anomaly. They will classify us not as a civilization, but as a short-lived perturbation in the background noise of the planet. And then, satisfied with their analysis, they will proceed to drill for the newly regenerated oil that has been slowly accumulating in the rock over tens of millions of years. And the cycle will begin again. This is the cruelest feature of the cycle, not the destruction, but the silence. Each successive civilization cannot hear the one before it. The physics of information storage across geological time prevents communication. Paper survives centuries. Stone survives tens of thousands of years, but we are trying to bridge gaps of millions of years. There is no material known to human engineering that maintains structural coherence for 50 million years on an active planetary surface. Even the nuclear waste markers we plan to build, those massive stone obelisks designed to warn future generations about buried radioactive material, will be ground to sediment by the next glacial cycle. Our most ambitious attempts at long-term communication will not survive even a small fraction of the relevant timescale. If a prior civilization understood this problem and wanted to leave a warning, how would they do it? Not through stone, not through metal, not through any external medium. The only information storage system that has demonstrably survived intact for billions of years is DNA. If a desperate civilization wanted to encode a message, a warning about the resource trap, about the carbon cycle, about the thermodynamic cliff that every industrial species eventually approaches, the only substrate robust enough would be the genome of a rapidly reproducing, adaptable organism. We carry, in our non-coding DNA, billions of base pairs whose function we do not fully understand. We assume most of it is evolutionary debris, but we do not know. We cannot read it. The sequence is there, the language is not. The silence of the past might not be emptiness. It might be a message we have not yet learned to decode. What does all of this mean for us? The Silurian hypothesis is uncomfortable because it dismantles a certain story we tell ourselves. The story that says we are the first, the only, the inevitable endpoint of 4.5 billion years of planetary history. The story that our civilization is uniquely important, uniquely permanent, uniquely capable of defining what it means to be intelligent on Earth. But if we are not the first, the implications shift in a direction that is, in a strange way, both humbling and clarifying. First, it means the Earth is not a fragile miracle that happened once by accident. If intelligence has arisen here before, the planet is not a one-time lottery winner. It is a machine that generates intelligence under the right conditions, repeatedly. The biosphere's resilience is not accidental. When the asteroid struck 66 million years ago with the energy of roughly 1 billion nuclear weapons, it did not end life. It disrupted the dominant forms of life, and within a geological eye blink, new forms filled the space. The biosphere does not collapse. It reorganizes. It evolves. It produces new experiments. Second, if previous civilizations existed and they burned through the accessible energy and collapsed, that is precisely what we are heading toward. And we are the first iteration of this cycle that might know it is happening. The previous tenants may not have understood what hit them. The troodontids, if they existed as a cultural species, may not have had the scientific framework to recognize what their carbon emissions were doing to the climate. We do. We have climate models. We have isotopic records. We can look at the Paleocene Eocene Thermal Maximum and see what 5 degrees of rapid warming does to a biosphere. We are not ignorant of the pattern we are in. Third, and most critically, the cycle creates a new ethical framework. We used to think of environmental responsibility in terms of preserving the planet for our children, a time horizon of a few generations at most. The Silurian hypothesis extends that horizon to geological time. If we burn all accessible fossil fuels, we are not just impoverishing our grandchildren, We are stealing the starter pack from whatever intelligent species comes next. We are pulling up the ladder behind us. If we scatter rare earth metals into the ocean, we are depleting the resources that a future civilization would need to bootstrap its own industrial development. We would be condemning the next intelligence to a permanent pre-industrial state, not through malice, but through short-term thoughtlessness. Our ethical responsibility, if we take the Silurian hypothesis seriously, is not just to survive. It is to leave the pantry reasonably stocked. This is where the uncomfortable reality becomes, paradoxically, a source of meaning. The cycle runs on the amnesia of its participants. Each civilization enters not knowing about the ones that came before. The trap works because the new species never sees the body of the old one. We are the first species in the known history of Earth that has the scientific tools to see the trap. We can read the carbon record, we can model the climate, we can sequence the genome and look for anomalies. We can look at the Paleocene Eocene Thermal Maximum and recognize our own reflection in it. That capacity to see the pattern we are in is not a minor feature of our civilization. It might be the defining feature. It might be exactly the capability that separates a civilization that becomes just another thin chemical layer in the rock from one that actually breaks the cycle. The cycle is real. It is written in the isotopes of ancient limestone and in the carbon excursions of deep time. But it is not inevitable. A wheel can be stopped, a pattern can be broken. Not by ignoring the physics, but by understanding it well enough to work around it. We are currently, as one framing puts it, in the awkward adolescence of civilization. We are powerful enough to alter the planetary chemistry, but not yet wise enough to do so sustainably. We are playing with matches in a library. But adolescence is not a permanent state. It ends either in maturity or in catastrophe. The previous tenants of this planet, whoever they were, whatever form they took, did not know they were in the trap. We do. And knowing you are in a trap is the first requirement for getting out of it. The research continues. Scientists are developing higher resolution tools for analyzing the isotopic record of ancient rock. They are refining their understanding of what a true industrial chemical signature would look like in the sedimentary record compared to natural geological processes. They are sequencing the non-coding regions of the human genome and other species' genomes with increasing depth, looking for patterns that natural evolutionary processes do not easily explain. They are developing theoretical frameworks for what different kinds of civilizations, biological, oceanic, distributed, would leave as their chemical legacy. The answer may never be fully resolved. The Earth is too efficient an eraser for us to find a city, a machine, a name. But we might find the chemistry. We might find the fever chart in the rock that says another intelligence once burned bright on this planet, consumed the easy energy, disrupted the climate, and disappeared back into the sediment. If we find that signal, it will not be a comforting discovery, but it might be the most useful one in the history of science. Because seeing the fate of the ones who came before us, written in the isotopes of 50-million-year-old limestone, might be exactly what it takes for us to become the first civilization in Earth's long, patient history to look at the cycle, understand it completely, and choose a different path. The room you are sitting in right now, the screen you are reading from, the walls around you, this moment, this experience of being alive and conscious and curious is not the first time something on this planet has felt this way. Somewhere in the deep past, another form of awareness sat in its equivalent of a room and wondered about the world. And somewhere in the deep future, if we do our work well, another will do the same. The chain is long, you are one link in it. What you do with that knowledge is the only question that actually matters. If this kind of thinking interests you, if you find value in content that takes science seriously and follows the evidence wherever it leads, consider supporting it. Like this video, subscribe, share it with someone who asks big questions. The thinking only continues if the audience does. We are still early in our understanding of deep time. We are still learning to read the rock. But every year, the instruments get sharper, the models get more detailed, and the questions get more interesting. The geological record is not a history of nothing. It is a history of everything that has ever happened on this planet, written in a language we are only beginning to learn. And somewhere in those layers, in the chemistry of ancient limestone and the isotopic ratios of old carbon, the answer might already be waiting. We just have to learn how to read it. There is something worth sitting with before we close. The Silurian hypothesis is not, at its core, a theory about the past. It is a theory about pattern. Patterns in chemistry, in thermodynamics, in the relationship between intelligence and the ecosystems that produce it. Every intelligence that has ever existed on Earth, if more than one existed, discovered the same fundamental problem. Energy is concentrated in certain places. Exploiting that concentrated energy creates complexity. Complexity is fragile. The more complex the system, the more catastrophic its collapse when the energy runs out or the feedback loops overwhelm the design. We call this civilization, but a more detached observer might call it something less grand. They might call it a temporary local reduction in entropy, a brief period during which matter organizes itself into increasingly complex configurations, uses the available energy gradients to sustain that complexity, and then, when the gradients flatten, disperses back into equilibrium. The universe does not seem to care particularly about complexity. The second law of thermodynamics runs in one direction and it runs inexorably. Energy disperses, order decays. Complexity is a temporary upstream swim against a current that never stops. And yet consciousness exists, curiosity exists, the experience of looking up at a night sky and wondering what else is out there, that exists. The feeling of reading about deep time and feeling the vertigo of scale, of realizing that the thin sliver of history you inhabit is almost immeasurably small relative to the history of the planet you stand on, that feeling is real. Whatever intelligence came before us felt something analogous. We cannot know what their version of wonder felt like. We cannot know if they had language, or music, or mathematics, or any of the specific tools we use to make sense of the world. But they were alive. They were aware of something. They experienced the world from the inside in some way that we, from the outside, separated by tens of millions of years of rock, can never access. That experience, whatever form it took, is gone now. There is no recovering it. The rock has closed over it. The mantle has recycled it. The signal is buried too deep for us to hear. But we are here, and we have the capacity, for the first time to recognize in the chemistry of a 56-million-year-old thermal event, a reflection of our own trajectory. The question the Silurian hypothesis ultimately asks is not whether something lived here before us. The question is whether we are going to do anything differently, whether we are going to be the cycle's latest victim or its first conscious survivor. We have the data, we have the models, we have the isotopic record of the past and the satellite data of the present and the theoretical frameworks connecting the two. We have more information about what is happening to our planet than any other species in the known history of the Earth. What we are still figuring out is whether information by itself is enough, whether seeing the trap clearly is sufficient to avoid it, whether a species that evolved to optimize for short-term reproductive success can retrain itself to think across geological time. The rock does not have an opinion. The carbon isotopes do not judge. The sedimentary record simply accumulates, layer by layer, indifferent to what it contains. Whether the next layer records a civilization that figured it out or another thin chemical anomaly that geologists will one day debate over is entirely up to what happens next. The science is clear on the timescales. The feedback loops that could destabilize the current climate are not on the scale of centuries, they are on the scale of decades. The window in which a civilization can course correct before the positive feedbacks become self-sustaining is not geologically long. In geological terms, it is almost immeasurably short. It is the next few years and decades. And yet, measured against the scale of what we are discussing, those years contain everything. They contain the entire question of whether this particular experiment in intelligence on this particular planet becomes a thin chemical layer in limestone or becomes something that actually matters across geological time. Researchers working on the Silurian hypothesis continue to develop the analytical tools needed to test it rigorously. High-resolution mass spectrometry on ancient sedimentary cores, isotopic analysis of biological signatures in rock layers that predate the known history of complex intelligence, theoretical models of what different technological trajectories would leave as chemical evidence. The work is slow and painstaking because the evidence, if it exists, is buried under enormous amounts of time and rock and geological transformation. But the tools are getting sharper every year. The samples are getting more refined. The analytical resolution is increasing. We are getting better at reading the language the rock is written in. Whether the rock has anything unusual to say remains, for now, an open question. And open questions are exactly where science lives best. The deep past is not settled. The geological record is not fully decoded. There are anomalies in the isotopic data that have not been fully explained. There are carbon excursions in the deep past whose sources remain debated. There are oceanic dead zones from 100 million years ago whose triggering mechanism is still not definitively resolved. Any of those anomalies might be entirely natural. The probability that they are all natural is high, but the probability that every single one of them has a fully satisfying natural explanation and that none of them represent the chemical residue of a prior intelligence is not 100%. It cannot be, given the scale of what we do not know. Science operates on probabilities and evidence. Right now, the evidence for a prior terrestrial civilization is circumstantial at best. The carbon anomalies have plausible natural explanations. The biological signals in our genome have plausible evolutionary explanations. The nuclear anomalies at Oklo have a plausible geological explanation. The hypothesis has not been confirmed, but it has not been falsified either. And the framework it provides, the idea that we should look for industrial chemical signals rather than physical artifacts, has genuinely changed the way some scientists think about the geological record. That is not nothing. That is how good science works. It changes the questions we ask. It changes where we look. It changes what we are willing to consider. The possibility that something was here before us, that something thought and built and burned and failed before the rise of mammals, is not a comfortable one. It forces a reckoning with our own position in the history of this planet. It forces us to take seriously the idea that intelligence is not a destination, but a recurring phenomenon, one that the Earth produces and then recycles with the same indifferent efficiency it applies to everything else. But discomfort is one of the most productive states a mind can be in. It means the model is being updated. It means the previous assumptions are being examined. It means the questions are getting bigger, and bigger questions, pursued with rigor and honesty, and the willingness to follow the evidence wherever it leads, are exactly what this moment in history requires of us. We are the species that can read the rock. We are the species that can look at a 56 million year old isotopic anomaly and ask whether it means what we think it means. We are the species that can hold the entire 4.5 billion year history of this planet in our heads simultaneously and feel the vertigo of where we fit within it. That capacity is not guaranteed to last. Nothing that this planet has produced has lasted in its specific form across geological time. But the capacity for understanding, the ability to decode the deep past and use it to navigate the deep future, that is the most extraordinary thing the biosphere of this planet has ever generated. And it would be a remarkable thing to waste. The geological record will continue to accumulate. The next layer of rock is being deposited right now, in the sediment of every river, delta, and ocean floor on Earth. That layer will contain our signature, the carbon-12 anomaly we are currently generating, the plutonium and iridium and rare earth metals we are distributing across the surface of the planet, the plastic-bearing rock formations that are already forming in coastal environments. Whatever intelligence reads that layer 50 million years from now will ask the same questions we are asking today. Was this natural? Was this artificial? Was this deliberate? Was there something here that understood what it was doing? We have the extraordinary opportunity, right now, to make the answer to at least one of those questions obvious. We understand what we are doing. The question is whether that understanding changes what we actually do. The Earth is patient. The rock will record the answer either way. Let us go back to the beginning of this inquiry and trace the full arc of what we have assembled, because the pieces connect in a way that is worth laying out completely. We started with a number, 4.5 billion years, a number so large that the only way to make it meaningful is to compress it, to collapse geological time into something the human brain can actually hold. When we do that compression, when we shrink 4.5 billion years into a single day, we discover that the window in which intelligence could theoretically have arisen before us is not small. It is the overwhelming majority of the day. We occupy the last 2 seconds of the last minute. The initial objection to this idea is physical. We would have found the evidence, but we established that this objection fails because it rests on a misunderstanding of how the Earth processes its own surface. The crust is not a static archive. It is a dynamic processor. Tectonic subduction melts ocean floor at a rate that recycles the entire sea floor every 180 million years or so. Erosion grinds continental surfaces down to sediment, which washes into the sea, which accumulates in layers, which are eventually subducted. The mechanisms of planetary recycling are so thorough and so consistent that even the most durable human-made structures, the pyramids, the Great Walls, the underground bunkers, would be unrecognizable within tens of millions of years and entirely gone within 100. The fossilization objection fails too. Fossilization is not a reliable record. It is a statistical anomaly. Of the 2.5 billion individual Tyrannosaurus rexes that ever lived, we have found complete or near-complete skeletons of approximately 30. The entire record of an intelligent species that lived on dry land, buried its dead in shallow soil, and lacked the habit of dying in swamps would likely leave no fossil record at all over the relevant timescale. Our own species will probably leave no recoverable fossils in 100 million years. But the planet has a memory that erosion cannot erase. The chemistry, the isotopic signature of industrial activity is locked into the chemical structure of the rock that forms during the period of that activity. The Suez effect, the shift in carbon isotope ratios that accompanies the burning of ancient biological carbon, is a permanent stain on the geological record. It cannot be washed away. It cannot be composted. It is the atomic barcode of industrial civilization. This realization transforms the search. We stop looking for shapes and start looking for ratios. We stop looking for artifacts and start looking for perturbations in the chemical record of the planet. And when we apply that filter, when we scan the climate history of Earth, not for bones and ruins, but for chemical anomalies, we find events. The Paleocene Eocene Thermal Maximum at 56 million years ago stands out most clearly. A sudden, rapid injection of light biological carbon into the atmosphere. A global temperature spike of 5 to 8 degrees Celsius occurring in what is, geologically speaking, a geological instant. Ocean acidification, marine dead zones, the collapse of bottom-dwelling ecosystems, and then, after tens of thousands of years, a slow, painful return to equilibrium. The natural explanation for this event is real and plausible. Methane hydrate destabilization triggered by orbital warming, but it is not without problems. The timing of the release, the isotopic signature, the rate of carbon injection, and the question of the trigger all remain areas of active scientific debate. The natural explanation is the default, and appropriately so, but it is not sealed. The PETM is the most compelling candidate event, but it sits within a broader pattern. Major carbon anomalies and thermal disruptions recur throughout the geological record at intervals that are suspiciously close to the recharge time of fossil fuel reservoirs. The cycle, if it is a cycle, runs on a timer set by the pace of geological carbon accumulation, each pulse lasting a few thousand to tens of thousands of years, each recovery lasting tens of millions of years, each new accumulation of easily accessible energy eventually producing a new spike in complexity. Whether those spikes represent natural climate processes, volcanic events, orbital forcing, methane releases, or something else entirely is the open scientific question. The Silurian hypothesis does not claim to have the answer. It claims to have identified a new way of framing the question. Instead of asking, why did the climate spike in the Paleocene, also ask whether a chemical signal of industrial origin would be distinguishable from the natural causes currently proposed. And if so, what would it look like? The scientists working on this question are not claiming a prior civilization exists. They are asking whether the geological and geochemical record would preserve the evidence if one had existed, and if so, what signatures we should be looking for. That is a rigorous, falsifiable scientific question. It changes what we look for. It changes how we interpret what we find. The question also opens into biology in interesting ways. The genomes of living organisms represent a form of information storage that has proven extraordinarily durable over geological time. We carry in our non-coding DNA billions of base pairs whose function we do not fully understand. The endogenous retroviruses alone, the fossilized remains of ancient viral infections integrated into our genome over millions of years, represent a kind of accidental biological archive. They record the history of ancient plagues in chemical form. They persist across timescales that dwarf any human-made storage medium. If a technological civilization had access to the tools needed to deliberately engineer this kind of biological archive, the information could potentially persist for tens of millions of years inside a host organism that continued to survive and reproduce. We are decades away from having the capability to do this deliberately ourselves. A civilization 1 million years ahead of us in biotechnology would have capabilities in this area that we cannot fully model. The question of whether our genome contains any deliberate encoding is not currently answerable. We do not have the analytical tools to distinguish deliberate encoding from the natural debris of evolutionary history, but the question is not inherently absurd. It is grounded in real capabilities that we ourselves are approaching. The nuclear record offers another potential channel of evidence. Certain radioactive isotopes produced by nuclear reactions have half-lives measured in millions of years. Plutonium-244, Curium-247. If a civilization used nuclear technology and the debris of that use was distributed broadly across the planet, traces might persist in the geological record for tens of millions of years, albeit at extremely low concentrations. The Oklo natural reactor in Gabon, discovered in 1972, demonstrates that nuclear fission can occur naturally under the right conditions. But it also demonstrates that a nuclear chemical signature in the geological record can have a natural explanation that makes it impossible to confidently attribute to artificial origin. This is the recurring challenge of the Silurian hypothesis as a scientific framework. Every signal it identifies as potentially diagnostic of industrial activity has a natural counterpart that produces the same signature. Carbon isotope anomalies can come from volcanic outgassing or methane hydrate destabilization. Metal concentration anomalies can come from asteroid impacts. Marine dead zones can come from volcanic-driven nutrient flux. Nuclear isotope anomalies can come from natural fission events. In each case, the natural explanation is at least as plausible as the artificial one, and in most cases, significantly more plausible given the rarity of intelligent life as we understand it. The hypothesis does not overcome this ambiguity. What it does is clarify the problem. It says, given the efficiency of geological erasure, given the fact that physical artifacts would not survive the relevant timescales, given the fact that the chemical signals we would expect from industrial civilization overlap with natural geological signals, the prior existence of a terrestrial civilization is almost impossible to confirm or deny. The absence of evidence is not evidence of absence, and the evidence we can look for is ambiguous, almost by definition. This is a genuinely interesting result. It means the question is real. It means it is not a pseudo-scientific claim to be dismissed, but a legitimate scientific puzzle that follows directly from what we know about geology, geochemistry, and the thermodynamics of industrial civilization. It also means the question may never be definitively answered from the geological record alone. What we can do, and what the researchers working in this space are doing, is to make the detection methods more precise, to develop better isotopic analysis techniques that can distinguish between biological and geological sources of carbon at ancient time horizons, to develop theoretical models of what specific kinds of pre-human civilizations would leave as chemical signatures and how those signatures would evolve over tens of millions of years, to look at the anomalous events in the geological record with fresh eyes and a more explicitly detection-oriented framework. The science is real. The questions are legitimate. The answers are not yet in. And in the meantime, we have the extraordinary privilege of being the species that asked the question, of looking at the geological record of our own planet and wondering whether the silence of the deep past is truly empty, or whether it is full of voices that simply speak in a language we have not yet learned to hear. That is where we are. That is the state of the inquiry. An open question about the deep past, studied with increasingly precise tools, generating new frameworks for understanding what we might find and what it would mean if we found it. The rock is patient, the chemistry is waiting, the isotopes do not change to accommodate our uncertainty. They simply are what they are, locked in ancient limestone and deep ocean sediment, holding whatever record exists of whatever happened here before us. Our job is to learn to read it. And if we are fortunate, and if we are wise enough to keep asking the questions long enough to find the answers, we might one day know whether we are the beginning of a new story or the latest chapter in a very old one. Either way, the reading matters. There is one more dimension of this inquiry that deserves serious attention, and it is perhaps the most philosophically challenging. It is the question of what intelligence actually is, and whether the universe cares about it. We tend to treat intelligence as a pinnacle, the inevitable product of billions of years of evolution, the highest output of the planetary system. We are the watchers, the namers, the builders. We look at the fossil record and see the long arc of increasing complexity bending toward us, toward consciousness, toward the capacity to ask questions about the universe itself. But the fossil record tells a more ambivalent story. The organisms that have survived the longest on this planet are not the most complex, they are the simplest. Bacteria have existed for 3.5 billion years with essentially no fundamental change. Sharks have been apex predators for 400 million years. Crocodilians have remained virtually unchanged for 200 million years. These are not failures of evolution, they are its most successful products. They found a stable configuration, and the planet has never produced conditions severe enough to eliminate them entirely. High intelligence, by contrast, is metabolically enormously expensive. The human brain, which represents roughly 2% of body mass, consumes approximately 20% of total caloric intake. To feed a brain that hungry, you need a rich, reliable, high-calorie diet. To maintain a rich, reliable diet across generations, you need stable agricultural systems. To maintain stable agricultural systems across centuries, you need a stable climate. To maintain a stable climate, you need to not burn all your carbon-based fuel in a few hundred years. Each dependency in this chain is a point of failure. The Silurian hypothesis, at its most challenging, suggests that high intelligence might not be a stable evolutionary strategy. It might be what biologists would call a maladaptive trait, one that provides short-term advantages but creates long-term vulnerabilities. A flash of complexity that burns bright, consumes the available resources, and then disappears, leaving the less demanding but more durable organisms to continue. Sharks did not need to build cities. They did not need to split the atom. They solved the problem of survival without generating the kinds of positive feedback loops that destabilize planetary chemistry. They have been doing this for 400 million years, and they are still here, largely unchanged, doing exactly what they evolved to do. We evolved to do something much more complicated. We evolved to model the world in our minds, to simulate possible futures, to build tools that extend our physical capabilities far beyond what biology alone can produce. This is an extraordinary capability. It allowed us, in a few thousand years, to go from stone tools to nuclear reactors to spacecraft. No other lineage in the known history of life has done anything remotely comparable on that timescale. But it also allowed us, in a few hundred years, to alter the chemistry of the entire atmosphere of a planet, to change the pH of the global ocean, to restructure the nitrogen cycle, to redistribute rare elements from stable geological deposits into the surface environment. No other lineage has done that either. These are not separate achievements, they are the same achievement. The same cognitive capacity that produced quantum mechanics and gene sequencing and orbital mechanics also produced industrial agriculture and fossil fuel combustion and nuclear weapons. The capability is not divisible. You get all of it together or none of it. The question the Silurian hypothesis poses, in its deepest form, is whether intelligence is inherently self-limiting. Whether there is a scale at which any sufficiently complex information processing system inevitably disrupts the environmental conditions necessary for its own maintenance. Whether the universe, having produced a briefly conscious observer, systematically eliminates that observer and returns the matter to simpler configurations. This is a version of the Fermi paradox applied to Earth's own history. The silence of the cosmos might not be because life is rare, it might be because intelligence is a phase, not a destination. A brief flowering that the universe produces occasionally allows to run for a few geological instants and then erases. The deep silence of the past would be consistent with this interpretation. But we are not yet at the end of our phase, and we have something that no prior species, if prior species existed, demonstrably had. We have a model of geological time. We have isotope ratio data. We have climate physics. We have the capacity, in principle, to see the pattern we are in from a vantage point that extends millions of years into the past. And we have, perhaps for the first time in the history of any intelligence on this planet, the possibility of choosing our next move with full knowledge of the context. Every game becomes easier when you can see the board clearly. Every problem becomes more tractable when you understand the rules. We are, for the first time, in a position to see the board and understand the rules of the game we are playing. The game that intelligence plays against thermodynamics and climate and resource depletion and the patient indifference of geological time. We have not won the game. We have not even determined how to win, but we can see it now in a way that no prior participant could. And that changes the odds. The Silurian hypothesis is, at its core, a story about perspective, about the power of situating yourself correctly in time, about what becomes visible when you zoom out far enough that your entire civilization, your entire species, your entire era becomes a single thin line in the rock. From that vantage point, the urgent problems of the day, the political conflicts, the economic pressures, the technological competitions still matter. They matter because they determine what gets into that thin line in the rock. They determine the chemical signature we leave. They determine whether the record contains the isotopic fingerprint of a civilization that understood what it was doing and changed course, or the same fingerprint we see in the Paleocene Eocene Thermal Maximum, the mark of a species that burned everything available and then went quiet. We know how to read that mark now. We have the tools, we have the framework. The question is whether we have the will to make our own record say something different. There is a final thought worth holding before this inquiry closes. Every civilization that has ever existed, every culture, every empire, every nation, every species that has risen to complexity and then collapsed has believed in some version of its own permanence. They built for the ages. They carved their names in stone. They established institutions designed to last forever. And they are all gone, or going. The stone is eroding. The names are fading. The institutions are transforming into things their founders would not recognize. This is not a tragedy. It is the nature of the system we inhabit. The planet produces things. The things exist for a time, the planet recycles them, and then it produces new things. The tragedy would be not to understand this while you still have the chance to do something about it. The tragedy would be to have the geological record in your hands, to see the pattern written in the isotopes of ancient limestone, to recognize your own trajectory in a 56-million-year-old climate anomaly, and then to proceed as though none of it matters because the next quarter's results need attention. We are, by any measure, an extraordinary species. We are the first known product of 4.5 billion years of planetary chemistry to sit down and ask whether we are the first product of 4.5 billion years of planetary chemistry. That is remarkable. That is genuinely unprecedented as far as we can determine. What we do with that awareness is the question the rock is waiting to record. The deep time is behind us. The thin layer of our existence is being deposited right now. And what the geologists of the deep future will find when they drill into our era depends entirely on what we do with the knowledge we have right now. We are the current chapter. We did not write the beginning of the story, but we might, if we choose carefully, have some say in how this particular chapter ends. And perhaps, in doing so, we might change the shape of the story that comes after. The rock does not rush. The sediment accumulates at its own pace. The isotopes decay according to their own half-lives. But we are not the rock. We are the brief, burning, improbable thing that reads the rock and asks what it means. That is the most extraordinary thing that has ever happened on this planet. And it is happening right now. It is happening in you, as you process this, as the patterns form in your mind, as the connections between deep time and present moment take shape. The universe is reading itself through you, for a little while. That is enough to matter. Let us step back from the philosophical and return, one final time, to the empirical. Because the Silurian hypothesis, whatever its larger implications, is ultimately a scientific proposal. It makes specific claims about what kinds of signals should be detectable in the geological record, and those claims can be tested. The most immediate area of active research involves refining our understanding of the Paleocene-Eocene thermal maximum itself. Scientists are drilling new ocean sediment cores from locations that were far from tectonic activity during that period, trying to get cleaner isotopic records of the carbon release event. The goal is to improve the temporal resolution of the data, to determine more precisely how fast the carbon was injected into the atmosphere and in what pattern. If the carbon was released smoothly and continuously over tens of thousands of years, the methane hydrate hypothesis becomes more compelling. If it was released in sharp pulses with abrupt onsets, the picture becomes murkier and alternative explanations become harder to dismiss. The current data suggests the release may have been pulsatile, but the resolution of the existing record is not fine enough to be conclusive. New analytical techniques are also being developed for identifying the specific isotopic signatures of synthetic versus natural, organic compounds in ancient rock. Modern industrial chemistry produces certain molecular configurations that do not appear naturally. If the thermal degradation products of synthetic polymers have distinctive isotopic signatures, it might be possible to develop a detection method that would identify artificial organic compounds even after millions of years of geological processing. This is technically extraordinarily difficult, but it is not in principle impossible. The rare earth element concentrations in ancient sedimentary deposits are also an active area of study. Understanding the natural baseline variability of these elements in pre-industrial geological contexts is important for establishing what would count as an anomalous concentration. The challenge is that the baseline itself might contain signals from prior industrial activity if such activity existed. The analysis is inherently circular to some degree, which is why developing independent lines of evidence from multiple chemical signals simultaneously is important. On the genomic front, the increasing capability to sequence and analyze large volumes of non-coding DNA is gradually illuminating the structure and history of what was previously called junk DNA. The endogenous retroviruses alone are a rich archive of information about ancient viral infections. Understanding the statistical properties of naturally occurring non-coding sequences, their mutation rates, their structural regularities, their evolutionary patterns, is a prerequisite for identifying any sequences that might deviate from what natural processes would produce. This work is ongoing and advancing rapidly, with improvements in sequencing technology and computational analysis methods. The work of searching for evidence of a prior civilization in the geological record is, in a very real sense, the same work as understanding the geological record itself more precisely. Every improvement in our ability to read the rock, every new analytical technique, every new core sample from a well-chosen location, every new theoretical model of what ancient climate events should have looked like, advances our ability to test the Silurian hypothesis along with every other hypothesis about the history of the planet. Science is self-improving in this way. The questions we ask shape the methods we develop. The methods we develop improve the questions we can ask. And occasionally, the new questions reveal possibilities that the old framework would never have generated. The Silurian hypothesis is, in this sense, valuable regardless of whether it turns out to be correct. It has already changed the framework. It has already led scientists to ask new questions about what chemical signals industrial activity leaves behind, and how those signals evolve over geological time. Those questions are important regardless of whether they were generated by curiosity about a hypothetical prior civilization, or by the desire to understand what signals our own civilization will leave in the future. The two questions are, it turns out, the same question. Understanding what a civilization leaves in the rock is understanding what we are leaving in the rock. The research into detecting a prior civilization is also research into characterizing our own planetary footprint across geological time. And characterizing our footprint is important, not only for satisfying scientific curiosity, but for understanding the long-term consequences of what we are doing right now. This is where the inquiry becomes fully circular in the most interesting possible way. We started by asking whether something was here before us. We developed a framework for what that prior presence would look like in the geological record. And in doing so, we developed a clearer picture of what our own presence looks like in the geological record. The exercise of imagining the detection of a prior civilization forces us to confront, with unusual clarity, what we are actually doing to the chemistry of this planet. The carbon isotope anomaly we are currently generating is the largest and fastest such anomaly in at least the last 56 million years. We are injecting carbon into the atmosphere faster than the methane hydrate releases of the Paleocene Eocene Thermal Maximum. We know this because we can measure it in real time. We can watch the isotopic ratio of atmospheric carbon change year by year. We are writing our signature into the geological record in real time, and we can watch ourselves doing it. A prior civilization, if one existed, did not have this vantage point. They did not have the scientific framework to understand what they were doing to the atmospheric chemistry until long after the feedback loops were already established. We do have that framework. We are, at this moment, watching ourselves write the chemical record that a future civilization or a future geology will read and try to interpret. The question of how clearly our signature will read depends on what we do next. If we stop the carbon injection now, the anomaly will be smaller, shorter, and potentially indistinguishable from natural events at the resolution available to future geologists. If we continue on the current trajectory and burn through the remaining accessible fossil fuels, we will generate an isotopic anomaly so large and so clearly differentiated from any natural event that it will be readable from hundreds of millions of years in the future. The clarity of our record, whether the next civilization can see us in the rock or mistakes us for a volcanic event, depends on choices we are making right now. That is perhaps the most concrete and actionable version of what the Silurian hypothesis has to offer. Not a story about the past, but a lesson about the record we are currently writing. Not a mystery about who came before, but a clarification about what we are leaving behind. The rock will remember, the isotopes will decay at their fixed rates, and the record will crystallize, and the sediment will accumulate, and the layers will form. And somewhere in those layers, our era will be represented by a chemical signature. It will be legible to a future intelligence with the right tools, if such an intelligence exists, or it will be one more anomaly in the geological record that a future science tries to explain, or it will be nothing, because nothing comes after. Which of those possibilities becomes real depends on what we do with the time we have. The geological record does not prescribe our future, it describes our past. And understanding our past, with the clarity that deep time perspective provides, is the best possible preparation for choosing a different path. That is the end of the inquiry. That is where the Silurian hypothesis leads when you follow it all the way through, from the geological mechanism of erasure, to the chemical fingerprint of industry, to the unsettling anomalies of the deep past, to the ethical implications of a cycle we might be the first to consciously recognize and consciously choose to break. The rock is patient, we are not. And perhaps that is why this question matters so much right now. We have a narrow window in which the choices we make will determine what the rock remembers about us. That window will not be open forever, but it is open now. Use it well. The questions we have been exploring are not just scientific curiosities. They are, in a very real sense, questions about identity, about what it means to be a technological civilization on an old planet, about whether consciousness, that extraordinary and improbable thing, is a stable feature of planetary systems or a brief anomaly. Consider what we know about the distribution of matter and energy in the universe. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Many of those stars have planets. The conditions that allow chemistry to become biology exist across enormous volumes of space. The conditions that allowed biology to become intelligence exist here, on Earth. Whether they exist elsewhere is one of the great open questions of science, but the Silurian hypothesis adds a layer to that question that is often overlooked. When we ask whether intelligence exists elsewhere in the universe, we usually frame it as a spatial question. Are there civilizations on other planets? But the Silurian hypothesis transforms it into a temporal question as well. Are there, or were there, previous civilizations on this planet? And if so, what can we learn from their fate? If the answer is yes, if the pattern of intelligence arising, industrializing, disrupting planetary chemistry, and collapsing is something that has happened here before, then it is far more likely to be a common pattern across the universe than if it happened only once. The Fermi paradox asks, where is everyone in the cosmos? One answer is that they all followed the same arc. They burned bright for a few geological instants, disrupted their planetary chemistry, and collapsed back into the geological background. The universe is not silent because life is rare. It is silent because industrial civilizations are brief. This interpretation of the Fermi paradox is called the Great Filter in reverse. Instead of assuming a filter lies ahead of us, a challenge we have not yet faced, it suggests the filter is behind us and repeating. Intelligent civilizations are not rare. They are cyclical. They arise, peak, collapse, and the record of their existence is erased by the very planet that produced them. If this interpretation is correct, the cosmic silence is not encouraging. It means we should expect the same fate. But it also means we are not unique in facing this challenge. Every civilization that has ever existed in the universe, every intelligent species that has ever looked up at a night sky and asked what else is out there, faced the same thermodynamic trap, the same finite resources, the same fragile dependence on atmospheric stability, the same positive feedback loops waiting to be triggered. We are not special in facing this challenge, but we might be special in being able to see it coming. Most species, most civilizations, most intelligent systems in the history of the universe probably did not have the analytical tools to look at the chemical record of the planet they lived on and recognize a pattern that extended tens of millions of years into the planet Denver past. They did not have mass spectrometers or isotope ratio analysis, or satellite climate monitoring, or global communication systems that could share a scientific paper across the entire planet within seconds of publication. We have all of those things. The combination of a global scientific community, precise analytical instruments, and increasingly sophisticated models of planetary systems gives us a kind of temporal awareness that no prior civilization on Earth if any existed, could plausibly have possessed. That awareness is the one variable that the cycle has never before contained. It is the new element, and new elements change what is possible. We cannot know whether we will use that awareness wisely. We cannot know whether the political and economic systems we have built will prove capable of coordinating a response adequate to the thermodynamic challenge we face. We cannot know whether the time available to us, the window between the beginning of our industrial era and the point at which the feedback loops become self-sustaining, is long enough for us to make the transition to a different kind of civilization. What we can know is that the attempt matters, that trying to break the cycle, even if we fail, is more meaningful than not trying, that the geological record would record the difference between a civilization that saw the pattern and chose its best course versus one that simply ran its program to completion without awareness. The thin layer of rock that represents our era will be readable. The chemistry will be what it is, regardless of our intentions. But the chemistry could be different depending on our choices. The isotopic anomaly could be smaller or larger. The duration of the carbon spike could be shorter or longer. The recovery time for the planetary system could be faster or slower. Those differences matter, not just for us and our descendants, but for whatever comes next. The planet will recover. It always has. But the shape of the recovery, the resources available to the next cycle of life and intelligence, depends on how deep a hole we dig before we stop digging. We are, right now, standing at the bottom of that excavation, looking up at the walls. We can see how deep it is. We have the measurements. We know the geology of the surrounding rock. We have the engineering capability to build a path out. What we are still debating is whether to start building. The Silurian hypothesis does not answer that question. It just makes it impossible to pretend the question is not urgent. It just adds the weight of geological time to the moral calculus. It just says, this has probably happened before, it did not go well, and you are the first iteration that can see that clearly enough to possibly do something different. What you do with that knowledge is your decision. And it is also, in a very real sense, the decision of everyone alive on this planet right now, making choices every day that aggregate into the chemical record the rock will hold. The rock is patient. It has been here for 4.5 billion years, and it will be here long after we are sediment ourselves. The patience of the planet is not a comfort, it is a context, an enormous, humbling, clarifying context. You exist in a universe that is 13.8 billion years old, on a planet that is 4.5 billion years old. As a member of a species that has existed for perhaps 300,000 years, reading about ideas that were published a few years ago and will be tested over the next few decades, the window is very small and very bright, and right now, that is where we are. That is who we are. That is the question the rock is asking. What is your answer?